the International Conference on Recent Researches in Mathematics. I'm so grateful to keynote speakers and research finding presenters who have been here among us for sharing us experiences and knowledge. Dear Justice, University, Mizan-Tepi University, located at the center of evergreen heart of Southwest Ethiopia. The main campus is headquartered in Viscous Zone, Mizan-Tepi town, 583 kilometers from capital Addis Ababa. Tepi branch is located 50 kilometers from the main campus in Tepi town, and the third campus hospital is located Tepi. A vision trying to be one of the 10 leading universities in Ethiopia by 2030. To put this into shape, we call up your invaluable hands to get together to support the success of our vision. I look forward to the years ahead, working with you to transform our concrete action. As we all know, research is crucial and driving force for the development of training, and therefore ample and sustained attention needs to be given so as to address the many societal questions that arose in minutes of time in alarming rate. Give justice and participation. This is a great opportunity for the mathematical community to interact. As we all know, mathematics is very useful in everyday life. It can help us do many things that are important in our everyday life. It is a universal language which is applied in almost every aspect of life. Besides,
Dr. Ahmed, you are muted. Please unmute your computer. You are not audible. Dr. Ahmed, you are muted.
hello.
Yes, you are muted. Yeah, now unmute.
Okay. Okay. Sama mana? Hello, good morning.
Good morning, sir.
Morning, sir.
Okay, ልጀምር?
ሌሎቻችሁ unmute አድርጉ, please.
I want to say a very good morning to everyone. And it is indeed a great honor and privilege for me to inaugurate the International Conference on Recent Researches in Mathematics. I'm so grateful to keynote speakers and research finding presenters to have you amongst us for sharing your experiences and knowledge. Dear guests, our university, Mizan-Tepi, is located at the center of evergreen heart of southwest Ethiopia. The main campus is headquartered in Bencheko Zone, Mizan-Aman town, is 583 kilometers from capital Addis Ababa. Tepi branch campus is located 50 kilometers from the main campus in Tepi town. The third campus, Mizan-Tepi University Teaching Hospital, is located at Aman. Mizan-Tepi University put a vision strives to be one of the 10 leading universities in Ethiopia by 2030. To put this into effect, we call up your invaluable hands to get together to support the success of our vision. I look forward to the years ahead, working with you to transform Mizan-Tepi University strategy into concrete action. As we all know, research is a crucial means and driving force for the development of nations, and therefore ample and sustained attention needs to be given so as to address the main societal questions and that arose in different periods of time in alarming rate. This is a great opportunity for the mathematical community to interact. As we all know, mathematics is very useful in everyday life. It can help us do many things that are important in our everyday life. It is the universal language which is applied in almost every aspect of life. Besides everyday life, there are various applications of maths that are useful for a wide range of academic subjects. Mathematics is important for all professions in the world in general. It is needed almost everywhere. Research conference on such issue is wonderful event in higher learning institutions to bring colleagues with common interest into one to know each other and share experiences. This is indeed an important occasion for all of us who have been involved in conducting research to solve societal and economic issues. Finally, I would like to extend my heartfelt gratitude to the members of organizing committee for realization of such a vital research conference. I would like to express my sincere wishes for success and blissful conference ahead. And with this remark, I declare that the conference is officially opened. Once again, I extend a warm welcome to all of you. Enjoy your participation. Thank you all for your attention.
Thank you very much, sir, for your thought-provoking inputs for budding mathematicians and briefing the Mizan-Tepi University. Now I will request to Dr. Temesgar Mekuria, Vice President, Business and Development to deliver welcome speech. Dr. Temesgar.
Okay, thank you, everybody. Listeners, dear participants and organs, welcome to this opening and ice-breaking and the first international conference on recent research on mathematics, hosted by Department of Mathematics, College of Natural and Computational Science, Mizan-Tepi University. I would like to thank Department of Mathematics, College of Natural Science and Computational Science, College of Natural and Computational Science for those who took this initiative and for their commitment and unbounded efforts in order to make this to happen. However, this conference is our first conference. Are you hearing?
Yes, you are audible.
Yeah. Okay. Just end. I'd like to thank every person in the department as well as the college who participated in this conference, and I would like to special thanks to the committee who took this initiative and took every responsibility and commitment, and for their great effort in order to make this happen in our university. However, this conference is our first conference and it's breaking. I hope that we will share each other a lot of precious recent ideas on mathematics, as well as gain an experience and motivation for our next conference we are going to host. Again, I'd like to thank all participants who accept our invitation and decided to participate on this conference, and thank you for your time and for your participation to participate in this conference. Lastly, I would like to say that I wish you all participants, and I hope we will have a nice time in our stay. Thank you very much, and thank you very much for everything. Thank you.
Thank you, Dr. Tamaslim, for your hearty welcome speech. Now I request Dr. Abiot Asras, Vice President, Research and Community Services, to address the gathering. Dr. Abiot Asras.
Am I audible?
Yeah, you are.
So I've shared one slide. I think, is it visible now? I've shared the slide. Is the slide visible to you all? No.
No, sir. No, sir. It's processing. It will take some time here.
Okay. So in the meantime, so Your Excellency, Dr. Ahmed Mustafa, President of Mizan-Tepi University, and the honorable keynote speakers, session chairs, guests, paper presenters, and conference participants from around all the world, ladies and gentlemen. So on behalf of myself, the Office of Vice President for Research and Community Services, and the University at large, I am pleased and honored to thank you all for joining us at our first international conference on recent research in mathematics being held virtually. So our distinguished speakers and participants who joined the conference from around the world make our conference truly international one. So for this conference, as have been remarked from the opening remark, so we have received many articles from around the world, and we have selected 53 papers to be presented in these 2 days conference across different sessions. So I would like to take this opportunity to pass my heartfelt gratitude to the International Affairs Directorate, Department of Mathematics, College of Natural and Computational Science, and the organizing committee members for their immense effort in planning and coordinating this event. So I am also thankful to the keynote speakers, the paper presenters, chairs, supporters, and presenters who devoted their busy schedule, and all the speakers who opted our conference to share their research outputs. So with this very brief remarks, so I would like to share you about the overview of our universities, research and community services. I think it's also vital to share this research, the university's overview of the different research and community service aspects. So is the slide visible?
Oh, it's visible.
Yeah.
It's not visible?
It's visible, sir.
It's visible, okay.
Make
So
it full screen.
Sir, make it full screen if possible.
It's already full screen.
Okay, you can continue, sir.
Okay. So I will be briefing you with our university's profile, and also I will also briefing with the grand research themes we have been undertaking, and also some of the research outputs that we have so far, and also the dissemination modalities that we have been held so far. So as has been in the speech of the university president, our university was established in 2007, and it is located about 580 kilometers away from Addis Ababa, the capital of Ethiopia, which is to the southwestern margin of the country. And the name of the university was coined from the two towns where the campus are situated, which was Mizan-Tepi. And the university is organized in the three main campuses: the Mizan Teaching Hospital, where Medicine and Health Science College were being undertaken, and also Tepi campus, where all the engineering and also natural and computational science has been developed. And these are some of the views of our main three campuses: the main campus, Amman campus, and that of Tepi campuses. And the university, our university's vision to aspire to be among the top leading universities in Ethiopia by 2030. And as a mission of the university have missions of providing and also providing relevant and quality higher education, and so conducting problem-solving research and rendering problem-solving community services to the community with engaging different community members. So these are our core values. So we value teamwork, we value innovation, we value collaboration, we value academic freedom, and we value accountability and transparency. So these are our core values, which is being shared by our students, our staffs, and also the whole management. So our university so far had 40 presidents, and this was the founding president was Dr. Mabratu, and I think the current president that have welcome speech, was the inaugural speech who made was Dr. Ahmed, and we have had only 4 presidents so far. So the university do have structure organized into the 4 vice president and also vice president status as a different campus heads, including the academic vice president, research community service vice president, admin vice president, business, and also the chief executive directors of the 2 campuses, which are AP and Amman campuses. So our university do have organized into the 6 colleges and 2 schools, and over which on these schools and the colleges we have had about 47 undergraduate programs and also 36 graduate programs, where we have so far graduated about more than 18,000 students, and currently we have enrolled about more than 17,000, and we are running these activities by having different academic staffs, over 1,000 academic staffs with different ranks have been doing both academic service and also research activities. So these are our main research thematic areas we have been running. So the first one was sustainable agriculture, environmental management, and bioeconomy, and mining, industrial manufacturing development, biomedical science, and we have 10 key thematic areas, of which I think mathematics do have a great role about all across all these thematic areas. It's a very vital in mathematics, mathematics department, and mathematics course. So far we have had about more than 400 projects, and we have about more than nearly about 100 projects undergoing, and these have been also increasing with the number of projects we are running across from time to time, and so the amount of budgets we have also enrolled incurring for research also increased from time to time. And as you see the projects across the different colleges, so almost the agriculture and the health science will have a great share, and include also engineering and natural and computational science, social science have this share about for the research undertaking in our university. So in publications which are in repeatable journals affiliated with our university is very much increasing. So as you see from this graph, the publication from year to year has been very increasing. So we have had about more than 600 publications, and those are only indexed in PubMed, Scopus, and Web of Science. And we might have about thousands of publications in different indexes, but these are those journals affiliated to our university, which was published in indexed and high repeatable indexed databases. So when you see the share of the research publications, so the majority of the share goes to the health science, which was those share about more than 50% share goes to the health science, and also 30% about natural computational science, including mathematics and other disciplines in the College of Natural Computational Science. And currently we are going to launch our journals, and the journal is going to be named Green Valley Journals, and this Green Valley Journal is to have a Green Valley Journal of Health Science, Green Valley Journal of Business and Economics, Green Valley Journal of Agriculture and Natural Science, and also Green Valley Journal of Natural and Computational Science going to be launched very soon. So we are establishing the editorial board and all the requirements for the journal establishment. So we'll be having this journal in the very near future. In terms of professional service, so we are providing service for healthcare services, for law services, agriculture, social science, natural services. So our academic staff, they are also undertaking research. Also, they are also serving the community surrounding this community with the different their professional services. So these are our hospital services, where our healthcare, the academic staff in the health science college do have to serve the community with the different clinical services and also public health services. And this also our free legal service aid, where we also provide free legal service for the poor surrounding the university community, where the staff in the law department at the law school also providing service to the population who are in need of the justice. So these are also different services we are providing to the educational service for enhancing educational access and educational quality. So we are providing different materials, also we are providing different trainings. We are also providing different capacity building trainings for all the academic staffs and the staffs at the high schools and elementary schools, so that we are enhancing and also we are improving the educational quality and access. So we have fully engaged in COVID-19 related services, particularly for prevention and the control of this service. As we have hospitals, so we have been very engaged in treatment of these COVID-related illnesses, and also we have been also highly engaged in preventing these COVID-related viruses, with particularly engaging our health science college staffs. So these are some of the evidence-driven community service projects. So one of the community service projects we have been doing was about multiplication and plantation of indigenous trees. So which is because we have been at the heart of the green, in as the motto of our university is the green, the green valley. That means so we are also providing these different indigenous trees in our area. So also providing and enhancing agricultural services by adapting different varieties and also providing for the different farmers surrounding the university, so that we are enhancing the productivity and production of the different agricultural products. We are also involved in animal production. So we have initiated a conservation mechanism for an endangered breed, which was very resistant to different types of animal illness and animal diseases. And so with the different production of meat. So we have with this we have also conserved these endangered species in our community. It's also one of the community services, or one of the technology transfer projects that we have had in our National and Computational Science College. We are also trying to come up with a different seed products with a different seed production techniques. So we have also different techniques of providing this technique with different other universities. So we are providing these seed products with different cones. So finally, we also have indigenous knowledge researches involving culture, history, and heritage management, and the language research, agricultural practice, health science, and the social sciences. So we have also different types of collection and range of different types of cultural museums or cultural elements of different societies around the university. And for this, we have organized an institute which is highly dedicated for doing research on indigenous practices. So we have had also different linkage with different universities and different offices in the local and also in the different international affairs. So we have had memorandum of understanding, also different activities with the different national institutions like Ethiopian Public Health Institute, Ethiopian Biodiversity Institute, the Chemical Industry Corporation, the different universities surrounding the globe, and including Colorado State University, where we are doing maternal health care improvement with the teaching hospital, the same power for particularly improving engineering, technology, engineering, and mathematics, and the universities and the different consortiums abroad. We have had also different international conferences and international training. So with virtually, we have had these different trainings. So we are also joining different consortium in surrounding universities to come up with the different research activities and services. So this was the same power, which is vital for particular for enhancing students' mathematical power, mathematical skill, mathematical knowledge. We have inaugurated this same power with the STEM center in our university, which was situated in Tepi campus. So where we are going to train the students from high school and the students from the university to enhance their skills and knowledge in science, technology, engineering, and mathematics. So this is also one of the ingredients and one of the vital aspects for the mathematics conference that we are holding today. So we have been also running different conferences. So far we have had about 10 successive conferences organized since 2012, and these are different grant teams where we have held deliberations for different conferences. And across these conferences, so we have had the number of papers presented across the conference is very much increasing. And recently it was about 28 in 2020. Even in 2020, we have had about 17 papers presented, and we are also planning to have a conference in the coming one or 2 months and for about this research conference. So finally, we have had a remarkable achievement attained over time in terms of student enrollment and in terms of increasing the capacity for enrolling different students and different graduate programs and undergraduate programs. And we have also we have different research and community service linkage with the different communities, and we have parts of different projects initiated and completed at different colleges, also in terms of the publication, in terms of the project initiation. So we have noticed the weak collaboration across different research and community services, and we have also, so with this we have inaugurated and organized the International Affairs Directorate, which is highly dedicated for realizing the linkage between the international affairs and international universities. And with this, I would like to thank you all for joining this conference, and also I would like to say this conference is going to be very fruitful and also for very special one. So I would like to say thank you very much, and I would like to say this is a very good conference, and thank you so much, and I wish a very successful and a fruitful conference.
Thank you, Dr. Abhyud, for giving a detailed review of Mizan-Tepi University. Now I request Mr. Sinthayo Gasio, Delegated Chief Executive Officer, Tepi Campus, to address the gathering. Mr. Sinthayo Gasio. Mr. Sinthayo, am I audible to you? Mr. Sinthayo?
Mr. Sinthayo, please unmute your computer and
አንድ ላይ አይደላችሁም እንዴ? ስንታየው ማለት ደውለታ ብዙ
yes, doctor. He is
ደውለት
coming. He is coming my office. Because of the internet interruption, he was out. Yeah.
Now let me call today's keynote speaker. Today we have one of the prominent mathematician and well-versed with able research activities, Professor Dr. Ramachandra Prasad. He is PhD in applied mathematics and he is working as a professor in the Department of Mathematics, School of Advanced Sciences, Vellore Institute of Technology, Vellore, Tamil Nadu, India. He has got PhD degree from Extra University, Tirupati, India in 2007 on the thesis entitled Radiation and Mass Transfer Effects on Convective Flow Past a Vertical Plate. Over the past decade, he has worked in the areas of multi-physical fluid dynamics and numerical simulation. His work has investigated complex phenomena of interest in mechanical engineering, applied mathematics, chemical engineering, and material processing. Fundamental contributions have been made by him in magnetic fluid dynamics, thermal radiation heat transfer, fluid modeling, micropolar non-Newtonian hydrodynamics, magnetic induction flows, viscoelastic liquid flows, porous media, and boundary flows. He has published more than 100 research articles, out of which 92 are published in SCI and Scopus Interest journals. He has published 6 books on radiation, heat transfer, thermodiffusion, and diffusion thermo effects, boundary layers, flows, and viscosity flows, and edited 1 book. 8 students got their PhD degree under his supervision in the field of computational fluid dynamics. His more recent work has involved non-Newtonian fluid dynamics, fluid particle suspensions, and lid-driven cavities. The numerical methods he has used is finite difference method, finite element method, network simulation methods, and finite volume codes for the solution of the above topics have been developed by him in the collaborations with US, Indian, Spanish, British, and Taiwanese researchers. He is presently a reviewer for 100 national and international journals. Now I request Professor Dr. Ramachandra Prasad to deliver keynote speech on computational fluid dynamics and Mach method. Professor Ramachandra Prasad.
So thank you, sir. Thank you very much for your introduction. Can you hear me?
Yes, sir, you are audible.
Yes. Thank you, sir. Thank you very much for your introduction and inviting me to this conference as a keynote speaker. And I thank all the officials of your university and also the department, and I congratulate the Department of Mathematics. And sir, can I share my presentation?
Sure, sir. It's visible, sir.
Sir?
Yeah, it's visible.
Thank you very much. So in the recent years, I have been working on computational fluid called as the Mach method. And cell method has been discovered and designed in the year 1965 by Harlow and Welch. The marker and cell method actually precedes the finite volume method, which was discovered by Patankar in 1971. And the finite volume method is more expansive and more useful to any engineering problems. But initially in 1965, the Harlow and Welch paper, which was published in Long Center in of California. And this method was a very useful method and still being used, and it is a more useful for regular geometries. The finite volume method is, of course, is a very good method and is being used very elaborately by all other engineering researchers, and it is used for irregular geometries, not only for regular geometries like square enclosures, square cavities, or rectangular enclosures, rectangular cavities. It is used for engineering applications with irregular geometries, real-time problems. But this is a fundamental method. Mach method is a fundamental method. Now, recently we have used this method and published many papers for my students, and I want to discuss this with the participants who joined here. You can use this method as a fundamental method. And first, you get acquainted with this method, and after that, we can go ahead with the finite volume method, the finite element method also. And this method, which is even being still used very widely, it is not that it is not being used, it is still being used. And but it may be used for regular geometries, but it gives you a very good amount of how that methods are, the finite difference methods are being used, and how that finite difference methods develop into finite element, finite volume, and finite element methods, and other aspects of discretization, and how that what is the difference between differential methods and integral methods. So the organization of this is that organization of this method is initially we discuss the fundamentals of the fluid mechanics, and after that we go ahead with the so initially that what is a fluid? what is a fluid before we start our work on fluid dynamics and also fluid dynamics.
Hello. David.
I'm requesting you all kindly mute your microphones.
Kasad. Ala يهتم هون
I request you all participants kindly mute your microphones. Mr. Afeberg, kindly mute yourself.
Can I continue, sir?
Yes, sir.
So a fluid is a substance that flows. So it is a substance which has a molecular structure and offers no external resistance to any shear force. And it is a substance which is being deformed by the slightest disturbance or a force that we use. So the materials which do not have this property is called as a solid. So the difference between the solid and a fluid is that the fluid gets deformed with the slightest force that we do a fluid flow. So there exist some materials which exhibit suggestive in some cases that solid. And the difference between a solid and a fluid is that fluid can be deformed by even by the slightest disturbance. Solid. Most materials can, however, be broadly classified fluids and solids. So if the fluids and solids put together, we call it as mechanics. So mechanics is broadly divided into fluid mechanics and solid. Now we study the fluid mechanics, which is the study of flow of fluids, and the fluid is one which gets deformed with the slightest force. And fluids can be broadly divided into two types, that is liquids and gases. It has intermolecular forces which hold together so that it possesses and it will not have a shape. And it has a slight compressibility, but it has its own issues with the Also, next is the gas, which is consists of molecules in motion which collide with each other, tending to disperse so that a gas has no volume or a gas dynamics is a separate in dynamics, and it is also so fluid dynamics in general is the science of motion of both liquids and we also use a word called as hydrodynamics. The word hydrodynamics is being used. This word is being used to describe this. Now, this word has been rarely used. Then we use the word fluid dynamics. Now, fluid, what is a fluid? And fluid is a continuum. Fluid, the velocity field, the stress field, the viscosity, the surface tension, description, and classification of fluids. Next is continuum hypothesis. Physical quantities associated with the fluid with a given volume element or assume it distributed continuously throughout a medium or within sufficiently spreads through a small volume in a very uniform way. And the Euler's laws of mechanics is a very well-known researcher in mechanics ought to be. So the fundamental principles are the principle of linear momentum, rate of change of momentum, body, and the principle of angular momentum, which is actually the moment of the momentum, the time rate of change of angular momentum of a body, torque on the body, where both torque and the momentum are being taken. Of conservation of energy, which we use derive the energy equation apart from the Navier-Strokes equation, and the principle of conservation of mass, rate of change of the mass body equals the rate at which it is being supplied. So in summary, the time rate of change of momentum of a body is equal to the rate at which the momentum is being supplied to the body by the application. Angular momentum, generally the angular momentum in Navier-Stokes equation comes when this micropolar fluid has come. The micropolar fluid equations has been described by by in 1966, and he used the angular momentum equations. He developed the angular momentum equations in 1966. A remarkable work. The change of energy of a body is equal to the rate at which the energy is being supplied. So the same is the case with the concentration. So what are the forces that we that on the body forces are the gravitational force, the electromagnetic force, that these forces are pressure forces. And mathematically, how we describe this fluid, and we describe the velocity of the fluid in 3 dimensions, and also for an unsteady flow, we take a very general case. So, equal to x, y, z in x, y, z spaces, and also time the fluid flow changes with time, we call it as unsteady. If it does not change with time, we call it as a steady flow. And the velocity is described in terms of a vector as u I plus vj plus w. Okay, that's a vector where I, j, k, or unit vector x, y. And the description of the fluid motion. How do you describe the fluid flow? And there are 2 types of motion descriptions that exist in literature. That is the Lagrangian and Eulerian descriptions. And the Lagrangian description generally, we keep track of the position and velocity of the individual particles, but that is not the case with the Eulerian description. So Eulerian description of fluid flow, we describe the position and velocity of a fluid in a flow domain or in a control. And we have to remember a very important point is that the Lagrangian description is very useful in solid mechanics. We go for the Eulerian description. The Eulerian description is very useful in fluid. So, if you describe the body forces on the fluid, the pressure field, which is again in terms of the variables x, y, z, and the t, velocity field x, y, z, t, the acceleration is equal to y, z. And so the velocity is u, which is a function of x, y, z, t, v, and w. So next we go to what is called as the derivative. The real derivative is a d by dt of dou by is equal to dou by, and the material acceleration is equal partial of v with respect to v dot del multiplied. The same is the case with the pressure. And the material derivative can be divided into the local derivative and also the advection term. And the next is the velocity field, which consists of steady and steady flows. You can have a 1-dimension, 2-dimension, and 3-dimension flows. And the initial aspects, initial basics of the fluid dynamics, that is timelines, path lines, and this is the stress field. Using this, we denote we derive the Navier-Stokes equations. The most important property of a fluid is the viscosity, what we call it as a Newtonian fluid, and stress is directly proportional strain and is equal to dynamic viscosity. The non-Newtonian is a slightly distorted version of this is the graphical representation of a Newtonian. It's always linear. Graph is very much, and this is the non-Newtonian pseudoplastic fluids, dilatant fluids, and the deformation rate directly proportional to this case of fluids, but is not directly proportional. It is multiplied by, it is powered by a minus. So the description of the fluid motion, the description of the fluid motion is becomes an inviscid flow, or call it as a real flow when the viscosity is 0, and it is divided into viscous, divided into laminar and turbulent. So compressible, internal and external. This is the graphical representation of the velocity. So this is the mathematics of fluid flow. So the del of del is a partial x, partial y, partial z. And the Laplacian operator is del square del dot del plus the second partial with respect to x plus the second partial with respect to y and the second partial with respect to z. And the gradient del p is partial of the pressure with respect to y and partial of p with respect to z. The vector gradient, divergence, and also the direction derivative. So the divergence is del dot u, and that is partial u plus partial u with respect to x plus partial v with respect to y plus partial w with respect to z. And the continuity equation, this equation has been derived using the conservation of mass. We don't go into any proofs. The divergence u is equal to 0. This is simple. I am just showing a very simple and the Cartesian form of the continuity equation. More complicated forms are also available in case of the fluid is not incompressible. That is in case of compressible fluid where density will come into place. This is a simple equation. So, and you can see that this is the Navier-Stokes equation for incompressible and the Newtonian, that is constant viscosity fluid. And from the conservation of momentum principle, Newton's second law of motion. So acceleration is equal to, so this is the kinematic viscosity term, action term, kinematic viscosity term, that is del dot u del u, the density term 1 by rho del p, that and the external forces. So one by one we will discuss. This del dot u del u is being noted as u del square u, and the next term is this is the acceleration term, that is the change time. Advection term, that is the force exerted on the particle by other particles of fluids. This is the velocity diffusion term. This describes how the fluid is being damped, that is highly viscous fluid. So some fluid, some air, fluid like air, which is air viscosity is less. The term that fluid flows in the direction of the largest change in pressure, that is LP. And next is the body force. External forces that act on the fluid. Maybe any term, that is, it may be a gravity term, it may be electromagnetic term, it may be a porous medium, or whatever. So the change in velocity with respect to time is equal to advection plus diffusion plus pressure plus body force. This is the conservation put together or equations. Next, according to the Newton's scaling of the Navier-Stokes equation, dimensional variables, we get a very important parameter of the Navier-Stokes equation, Reynolds number. So, writes whether the flow is a laminar or a turbulent. Find this equation. So this. So Euler's equation. The Euler's equation is where the Reynolds number tends to infinity and the stress term vanishes. So where the viscosity becomes a zero. This is an ideal equation. Is said to be inviscid, where there is no viscosity. And spelling of the Navier-Stokes equation is what Bernoulli's equation in case of the boundary. Quantities of the Navier-Stokes equations for the local and steady flow. You can use the many geometries like pipe flow, plate flow, the steady laminar flow. You can have a steady laminar flow and the plate impulsively started, or any other plate ground layer, airfoil flow. Airfoil flows, that is the flow on an airplane wing. Next is a pipe flow where the flow is inviscid and also impulsively started. Steady viscous flow of a cylinder, airfoil of an unsteady flow. And I have also given the local acceleration, convective acceleration, the pressure gradients, and the viscous forces, how it is being present. So these are the general, the continuity and the Navier-Stokes equation for an incompressible Newtonian fluid in Cartesian coordinates. So you can see that the continuity equation is a partial x, partial of u with respect to x plus partial of v with respect to y, and partial of w with respect to z. Component, y component, and z component of the Navier-Stokes equations. Navier-Stokes equation. All three. This is the continuity and the Navier-Stokes equations in of non-Newtonian incompressible non-Newtonian flow of Newton. This can be used for axisymmetric flows and modeling of the Gaussian equations in 3 dimensions, continuity equation of state, and also the Rayleigh equation. And this is the modeling of coordinate system. So Cartesian coordinate system, cylindrical and spherical coordinate. Flow visualization is a very important part of the fluid dynamics. And in case of any other method, whether we use the boundary layers, whether we do not use the boundary layers, or we solve the equations in case of a Mach method or a finite element or a finite volume method, we have to draw the streamlines, isotherms, and so streamlines and stream tubes. This is the streamlines. So the streamline is a curve that is everywhere tangent to the instantaneous local velocity vector. And the streamline is written like this: R is equal to psi plus yj plus zk, that is a position vector. And the geometric arguments in this case, streamline is dr by dr over v is equal to v and dz. These are the examples of streamlines in a car. It's a path line. The path line is the actual path traveled by the vehicle period of time. And streak lines, it is actually the locus of the fluid pass sequentially in a prescribed point of comparison. Flow, path lines and streak lines are are some of the properties of the important property that we consider in case of aerodynamics is the drag force. That is, the drag force, the surrounding fluid exerts a pressure on the viscous. This is what is theory, a famous theory until in the year 1904, and it became famous after some time, being used very widely in case of aerodynamics. So the prediction of the drag terms, and this is the viscous boundary layer. Boundary layer is one where the viscous, where the by taking the Navier-Strokes equation, shear stresses, the viscous shear force is being felt very close to the surface of the body, and the viscous forces are not being taken so seriously and felt very close to the only close to the body. So that is where the viscous shear stresses are being felt. We also call it as a thin boundary layer flows, and which is very useful in. So this is the moving plate boundary layers, and this is a very small boundary layer thickness elevation. It's in a flow separation in a boundary. Also separation at sharp corners in case of a moving truck, and flow separation in a diffuser with a large angle, and separation in case of the adverse pressure gradient is adverse, then the flow separation takes place before we actually expect. Turbulent boundary layers. Some other will airfoil, the effect of the angle of attack, airfoil and the shape of the airfoil, the suction is very important in the airfoil. So you can see here that this is a very simple case of of the boundary layer, and this is called as the viscous zone and the inviscid zone, where the effects of viscosity are not being felt. Region, the viscous region, is called as very clearly that the transition from the so a wake is being formed. Adverse pressure gradient leads to separation, and it is and some other theories. So geometry, the geometry and shape of the working system is very important. Simple geometries can be easily created by some geometric parameters like plates, circles, pipes, and also the complex geometries should be described using the equations. Modeling of the flow conditions where the parameters are being very important are Reynolds number and Mach number, and also some other numbers like the initial conditions. You know that initial conditions and the outlet for the turbulence are also being available. It is a DNS, direct numerical simulation. Most accurately is being used, being solved to Navier-Strokes equations. Very expensive for the DNS, Reynolds average, Navier-Stokes equations, where the efficient boundary layer, but excessive diffusion is large eddy simulation systems, accurate and separation region is a direct simulation. So CFD, that many people think that CFD is computational fluid dynamics. So CFD is a simulation of fluids in engineering systems using the numerical methods. Many solvers have also come, numerical parameters, grid generation. So we can see from over a period of time that the capacity of the computer, capacity of the hardware of the computer now, what has been a homework problem now in the 21st century would have been a PhD thesis in 40s and 50s. So this is the development of the fluid dynamics, development of the hardware of the computer, which helped us in computational fluid. So the simple problems can be easily solved. Where CFD being used in aerospace, automotive, chemical processing, heating, ventilation, and air conditioning, hydraulics, marine, oil and gas power generation, and also being sports mechanics these days. Sports mechanics has not been fully developed in sports mechanics is a very important part of modeling is the mathematical physics problem in terms of the initial and the boundary. IBVP is a form is in the form of a partial differential equation. Includes geometry and domain of the problem, the coordinates, the governing equations, flow conditions, initial and boundary conditions, and selection of models applications. Numerical method. So the problem is that which numerical method that we have to use to solve a particular boundary value problems or discretized into algebraic equations using the numerical methods. The numerical methods includes discretization methods, solvers and numerical parameters, grid generation and transformation, high performance and post-processing. So discretization methods is a finite difference methods, finite volumes and finite element methods. Finite element may not be a discretization, but it's an integral method. This discretization method has explicit and implicit methods. Nowadays, nobody is using the explicit method. There is a question mark about its stability, preconditioning. Solvers, of course, the solvers are very much available. Cramer's rule solvers, Gaussian. You can find these solvers anywhere, even in the internet also. So numerical grid. So numerical grid will be very convenient and very easy if it is a regular geometry. But in case of geometry like an airfoil, this will be very difficult to go for an unstructured grids. Some very good have come. These are the softwares that which is being used by commercial researchers in GridGen, CFD. What is the process of the computational fluid? So the purposes of CFD codes will be different, and for different has its own application. The code will depend on the problem. So geometry, physics, mesh, solving and reports and the process. This is the process of CFD. So I don't want to go into this entire process. So geometry, physics, mesh, solvers, reports, and post-processing. Geometry, the selection of the appropriate coordinates. So determine the domain, shape, size, and shape. Any specifications which are needed, we have to for any commercial code. We can use the commercial codes if it is applicable, or otherwise we have to write our own codes. Next, physics of fluid flow, that is a flow condition. We have to see whether the problem is inviscid, that is where the viscous zero viscous flow, laminar flow, or turbulent flow, or any other flow fluid properties like viscosity, thermal conductivity, and we have to look into all these aspects. So these are the explanations of mesh, also solves. And what is the method? Finite element methods. Now we are not going to discuss the finite difference, we will discuss. So before we go to the finite, so we will discuss a brief discussion about the partial differential. So partial differential equation is an equation involving the partial derivatives. The general equation of the discriminant is less than 0, it is called as an ellipse. Equal to 0, it is parabolic, and if greater than 0, it is said to be hyperbolic. Examples are Laplace heat conduction equation and wave equation respectively. If you, this is the heat equation, famous heat difference and discretization method. So this, the introduction to finite difference is that use the Taylor's theorem to derive the finite differences, and this is the discrete grid points in the finite equation. So you can see that these are the grid points. We call it forward difference, backward difference, central difference in case of the derivative, and this is the second derivatives of a central, forward, and backward differences. And these are the derivatives of mixed derivatives. That is where the derivative is with as well as with respect to y. So central difference, forward difference, and backward difference. And these are the as for and this is the geometrical understanding of a forward difference. This is the true derivative. You can see that the derivative is a tangent to the curve, and the approximation goes like this. In case of the forward difference. In case of the backward difference, the approximation will be xi minus 1 to this is the case of the that it will be from xi minus 1 to xi. Very important thing that it is always better to use a centered. Us forward, backward, and now we go to the simple method called as the marker. And before we go to the marker and cell method, so we simply see on a straight line that how that grid points are being located. So this is the grid point I minus 1, I 2, I plus 1, standard collocated grid. And collocated grid where odd and even decoupling takes place. Minus 1, I and I plus 1. There is a very fair possibility of decoupling in case that we write the. So the combination of collocated, that is velocity, and the coupling of nodal values of odd and even nodal value. Decoupling is being addressed in case of a staggered grid. So please have a look at this staggered grid on a straight line. So now what we do is that we place pressure on I minus 1. Next, we place pressure on I minus 1 by 2 in case of velocity. After that, we place pressure I and I, and we place the velocity in I plus 1 after that. This is a staggered grid. Odd and even decoupling. This is the of the MAC method, what we call it as marker and cell method, which is originated by Harlow and Welch in 1965. And this is a staggered grid in case of dimensions. So please have a look at this. This is the pressure cell is being placed. The U term on the axis and the V term on the axis. And this is the pressure place. This is the pressure I minus 1 and the pressure I plus 1 term, and the velocity terms are being placed to the west. And so using this in 1971, Gortling and Suhas Patankar has derived the finite volume. So what are the advantages of the MAC method? So MAC method requires no interpolation. The variables are being stored very well, exactly where they are needed. No odd even pressure decoupling. So in case of the Navier-Strokes equation, the most difficult part of the Navier-Strokes equation is how to deal with the pressure gradient. most important thing. So if we fail to deal with the pressure gradient, that is a dou p by dou x, a partial p with respect to x, a partial p with respect to y, then we can never have a good solution. And the disadvantages is also there, as I already pointed out, that some disadvantages of marker and cell method is it's a fundamental method, of course. It always will have an advantage over the previous methods, and when it comes to the any method that is finite volume or finite element method, which came after the marker and cell method, and tried to overcome the disadvantages of the MAC method. So the disadvantages are added geometrical complexity from the multiple sets of nodes and control volumes. So geometrical complexity, it cannot deal with the geometrical complexity. It is difficult, and I am not saying that you cannot deal. We have also published a number of papers using the MAC method, where we used some trapezoidal enclosures and also the triangular enclosures by using the MAC method. We can still use it, but it is quite difficult to code. Coding will be difficult, and we faced a lot of problems in case of MATLAB. And if you take the Navier-Strokes Navier-Stokes equations of incompressible flows, that is that the unsteady term is there, the convection term is there. On the right hand side, you have a pressure term and the viscous term with respect to the u velocity. So the equations are there with respect to the v velocity. And they're transformed into non-dimensional form using the dimensional parameters. You have you can see that there is an unsteady term and also convective term is equal to the pressure term, and also you have got the Reynolds number multiplied by the viscous terms. So we write down the viscous terms as d is equal to 1 by the Reynolds number, 1 over Reynolds number del square u, and we write down the advection terms, that is the convective terms, as u multiplied by del dot u. So we write down this as the term as un plus 1 ij minus un ij over delta t is equal to minus an ij minus del pij plus dn ij constraint on the velocity. And there is, you can see that there is no explicit equation. So split that and we write it into this, while the second equation, that is ij minus un ij over delta t is equal to minus an plus dn. And this is equal to, again, un plus 1 minus ut by delta t, introducing a temporal velocity in the projection. After that, we derive the equation for pressure and we take the divergence off, and we write down this as un plus 1 ij ut minus I into delta t. Like this. First, we find the temporal velocity using the advection term and the diffusion terms only. After that, we find the pressure needed to make the velocity field incompressible. And we correct the velocity by adding the pressure gradient. After that, we add the pressure gradient to the Navier-Stokes equation. This is the solution algorithm of MAC method. That is the initialization of u, v, and p, discretize these all and solve the momentum equation, calculate the divergence, calculate pressure from Poisson equation, and update the velocity and pressure, check the convergence, and after that we repeat the step. We have taken up the very general equations, and this is the the discretized equations. So because it is very tedious, it takes a lot of time to discretize, and also this is the staggered. Also shown this staggered grid in case of a fully implicit equation. This is the complete discretization of the unstable dimensional incompressible flows. Newman analysis, we derive the stability. array equation. This is the and also pressure calculation. After that, we introduce the pressure calculation in velocity. We correct the velocity and we update the velocity. Please.
Thank you so much, sir. We are enlightened with latest evolutions in computational fluid dynamics through your keynote speech. We are very much thankful to you for participation in this conference. Now we are going to start paper presentations. I request all the participants kindly mute yourself, and if you have any question, please type the question in chat box. After completing the presentation, presenter will answer your all questions. Also, my humble request to all presenters to finish the presentation within the time allotted to you. Now, our today's first presenter is Professor Muharram Ali Khan from Department of Mathematics and Statistics, Umaru Musa, Yar-Adua University, Katsina, Nigeria. His title of presentation is Contributions to Commutativity Theorems for Certain Rings via Multiplicative Generalized Derivations. Now I request Professor Muharram Ali Khan to present his noble work. Professor Muharram Ali Khan. Professor, am I audible to you?
Yeah, I'm just
Okay.
Okay. Yes.
Professor, please share your slides.
Mute, sir. Sir, Muharram Ali Khan, unmute yourself.
Professor, am I audible to you? Professor Muharram Ali Khan, are you there, sir?
I'm there. I'm just 1 minute, please.
Okay. He's sharing.
Okay. Okay, sorry for interruptions, please. That's starting to my just
Professor, I request
yeah.
you to please make it full screen.
Okay, yeah, thank you. You have seen my
Hi there, Professor. I want to ask a question, please. Sorry.
Ma'am, we will give you time in the last.
just when I start, please, just 1 minute.
I have a
I
presentation
can start with there.
in
No?
this session or another one.
Hmm? Yeah, yeah.
I think schedule is already sent to you. You can
The
check there.
schedule I have, yeah, that's I have seen it, the schedule, and I've just. I can start now, please, right? Hmm.
Yes, sir.
Okay, thank you. Hmm. Okay. As you see this one, we start from commutative contributions to commutativity theorem for certain rings via multiplicative generalized derivation. This is the title of my topic. So what is the questions will be here? The first question is what is the ring theory? Second question is what is the commutativity for this for rings now? And third one, how to make the commutativity by using this is a suitable derivations such as multiplicative generalized derivation. So in this talk, we are just concentrate about multiplicative generalized. So first we start from what is the origin of this one, what the contents will be here, which I divide. This is the second slide. First I will write abstracts, as we've seen it here. Secondly, the origin of ring theory and special class of rings such as prime rings and semi-prime rings and associative rings. And second topic is here, commutativity theorem, how we impose commutativity on rings will be here. So we can make this system as a commutativity theorem for rings and its extensions. And third will be there, derivations and its extensions. And after that, this is multiplicative generalized derivations on semi-prime rings. So first we separated the result on associative rings. First we take the associative ring and then apply multiplicative generalized derivation to get the result. Secondly, we prove some theorem, the commutative theorem, on semi-prime rings using the same multiplicative generalized derivation. Thirdly, some related results, remarks and example to justify our results. And finally, this is the open question, conclusion, and references. So just to come by, this is abstract as you have seen it. This is the abstract. Here in this abstract over here, the result will be here associative rings. Involving means this is equal to, first we take the associative rings and we define the properties of this algebraic or differential properties, like the condition number C1, C2, C3, and this is your C4. This one, that's the result. And then we can apply the multiplicative generalized derivation on this range under using these conditions. Then we prove this is commutativity over there. And this one, and the third slide will be here, next one. Yes. Yeah, this is the origin of ring theory. It starts from this one work of Dedekind in 1870. Dedekind proved that the factorization properties of integers extend to algebraic integer if elements are replaced. These elements are by ideals, gave the word ring, ideals, and field. The modern theory of rings was developed in 1920s by Eminathar. In 1921, in Eminathar's, the best papers of this one, the theory of ideals and rings, revealed that a ring is a system closed under two abstract operations, addition and multiplication, to which he gave the name of the addition and multiplication with these operations are required to 6 axioms. So these 6 axioms are at that time in 1921. Why we call it abstract algebra? So the associative law of addition, commutative law of addition, associative law of multiplication, the commutative up now from the fourth. It is started to the another part will be here. The commutative law of multiplication, distributive law for multiplication over addition. This is these two things will be here, and the three and to make the two different will be systems now. Addition and multiplication, as you see, the associativity condition there. And the last one, 6. For any A, B in R, there exists a unique element X satisfied the equation A plus X is equal to B. So from this solution, we can say about the identity, we can prove it easily, but because of this time will be here, we can prove this. 0 is the identity of the addition, and this is the minus A will be the inverse of this will be here. And then they have divided the two port of these rings, non-commutative rings and commutative rings now. So that will be here. From this definition, the study of ring was transferred into a powerful theory, and the pillar of modern mathematics that is known as abstract algebra. Today, commutativity of multiplication is not part of the definition of a ring. So that's why we are studying the commutativity theorem. So next step will be here. Next slide. So this is the method. This will prove how to R is under addition, this is group addition. So that we have proved that the plus is your 0 is the identity element of the under operation addition, and minus is the inverse addition. In 1930, when the modern algebra, abstract algebra become one of the main branches of the mathematics. Now this type of work what we are doing, a mathematics generalizations and extension. A mathematician like a painter or poet is a maker of patterns. If patterns are more permanent than there, it is because they are made of ideas that is given by G.H. Hardy, 1877 to 1947. So after this, we have started what is commutativity theorem. Special classes offerings, as I told you, this one is the prime ring, and this is the definition of this one and their characterizations over there. Here ring R is said to be a prime ring. If you take two elements of there, then X or Y 0, then this implies that either X is 0 or Y is 0. So if R is a commutative ring, then R is prime if and only if R has no zero divisors. So these are this is a ring or is a semi-prime if for any X belongs to R, X or X is 0 implies that. So this means that a ring is a semi if and only if R has no non-zero nilpotent ideas. So these the definitions are given in the nilpotent elements over there. Up next step will be what is the commutativity theorem for rings. Since the late 1940s, shortly after the development of the general structure theory of associative rings, applications say to commutativity theorem, that is, if you can see the reference in Jacobson structure ring in 1964. Recently, there are several results dealing with condition under which ring is commutative. Then our target is here, how can we get that commutative in a non-commutative ring? Generally, such conditions are placed on the ring itself, or its subset, or its commutators. So commutativity theorem are part of the study of binomial identities in non-commutative rings. They are theorems which assert that under certain conditions, the ring at hand must be commutative. And the proof is the several will be here. Either we can use the algorithm will be there. To continue, this is the first theorem in 1905, Wedderburn proved that a finite division ring is a necessary field. Actually, from this result, in 1945, Jacobson, he thinks about this between division ring and field, what is a gap? So there is a gap of only commutativity here. So that is will be here after 40 years, Jacobson first proved in his paper, this result will be here. So next one, Jacobson, let R be a ring in which for every element L, so there exists an integer such that an X is 0, then R is commutative. So at that time, Jacobson pointed out that he was interested to prove for a fixed N, but during the conversation with Professor Kaplansky, he suggests that the general value of N, that is N depend on X will be here, so he calculated this will be here. That result is also very interesting. Then Kaplansky, he said, see from here. The first condition R is a simply ring in which for every there exists an integer N is depend with the elements of X greater than 1 such that Nx is equal to, then R is commutative. Then Kaplansky takes this is Xn is belongs to center only, not equal to X. So that is called a K rings. and this is a Herstein proof xn minus x in center. So then it is commutative now. So this is the beginning will be here. After that, we come back to our derivation and extension. So this is we are going. What is the derivation? So derivation is simply a map. G is additive map first. So G x y like homomorphism or endomorphism, automorphism, Gx plus y, equal Gx plus gy. If you can put the multiplication, this addition is here, and then the second additive map is called a derivation if Gxy is equal to Gxy plus xgy for all xy belongs to the. An additive map G on R is called a generalized derivation. If there exists, if G will be a generalized Gxy plus x of gy. Here G is your derivation now. So this capital J is your generalized derivation, small g is your simply derivation now. So a map M or up C, just to remove the additive condition from there, then we can say it is a multiplicative derivation. A map F from R to R is said to be multiplicative derivation if mxy plus xmy is same. If you replace M by this one, if you can add additive condition here, additive mapping, it just become a derivation. But if you remove the additive condition, then you can say multiplicative derivation should go there. Now the multiplicative generalization, the concept of multiplicative generalization work in 1991, which was inspired by the work of Martindale. In addition, there is some example they are used are important, but due to short of time, we cannot go details about this. So a multiplicative derivation of R is a map of C from here, satisfied that mxy of this are defined. The concept of multiplicative generalized derivation was given by Diab in 1971. Up here, if you can see, there is no bracket between generalized derivation. So that's why let G be a map, not the additive map, and D is a derivation. And then if a map Gxy plus Gxy is equal to, this is the capital G, I'm sorry, this is not the small. So this one, please correct it here, capital G. Gxy plus x dy hold for all xy are, then G is set to multiplicative generalized derivation associated with D. Now the natural question arises here, can we take D as a map instead of a derivation? Then we have to define the next step. You come here in 2013. This is equal to 2013. Dara and Ali, he proved that let G be a G from R is said to be a multiplicative generalized derivation. That the bracket over here. If there exists a map G from R to R such that Gxy is equal to Gxy plus xgy, here the small g is not a derivation, it's just simply a map, even not an additive over there. So a natural question arises from here, when a multiplicative derivation additive was answered by Diab was motivated by the work of Martindale and introduced the notion of multiplicative derivation as I have defined earlier now. So for using this thing, we have defined our results. We have defined all the identities, if you can see the abstract. So here, what is our first target is here. If we can assume that R is a ring and D is a multiplicative of this associative ring, is a non-commutative ring, keep in your mind, and T is a multiplicative derivation, so derivation T, if further satisfied either this, then we can say that this set A, what we have defined, AY is a multiplicative derivation, generalized derivation associated with G. Then the theorem number 2.2, so this is the proof is already there in the paper, so there which I have submitted. So please you can see there. Let R be, if you have any question from the paper, you can ask me now. Let R be an associative ring. GB, I have taken the here AY, here BY. Just see the identity, xn, xy, xm plus gy. Here we have taken plus minus the same y and just replace because there are no commutativity is here, so we cannot. So we take the different two identities here, minus plus y and xy here. Then also we prove that these are the basic things over there. Then we come to the theorem on semi-prime rings via multiplicative generalized. Suppose that R is a semi-prime ring, Z is a multiplicative generalized associative with a generalized derivation satisfied with the map G. I satisfied either the condition C1 or C2, then G is equal to 0. Yes. So theorem 2 will be here, C3 G is equal to 0, and this is equal to theorem 3, the semi-prime ring and multiplicative, and then theorem 4 will be here, same prime ring, the 7 and 8. All the conditions we prove like this. Actually, now the question arises, how can we say about commutativity of this will be here? So let us start from there, because we proved the theorem 4.1 related result. Suppose R is a semi-prime ring and satisfied this condition, look from here, this one, xm plus 1 for all and this, then gx x equal to 0 for all x belongs to R. Suppose that similarly the second paper, second result will be there same under the same conditions. See what is the commutativity here. According to this lemma, these two references given there, each multiplicative generalized derivation associated with the map G is a multiplicative derivation. In addition, if G is additive map on R, then every multiplicative derivation becomes the multiplicative generalized derivation on same prime ring R. In this corollary, we prove that let R be a prime ring and G be a multiplicative generalized area associated with non-zero derivation D. If R satisfies theorem 4.1, 4.2, then R is commutative. This proof is very easy, will be here because this is, we can go back to the Bell paper, it will be here 1991, and then we can easily get the proof. The proof already I have given corollary. And this is the example we justify. You look from here, if A is not equal to 0, this is then ARA, but definition of the same primary. If ARA is equal to 0 implies that either A0 or, so this is implies the same primeness, but the condition all of them is satisfied. But this is, that's why it is this one, this semi-prime condition is essential for this one. And this is the open problem. Look from here, as I told you, this is the first Jacobson paper and the Harstein and Kaplansky. They prove the same wet extension will be here. All the results I have done, because this is the problem, open problem. I gave this one. This can be proved in the center. Everyone will be center, P1, P2, P3, and P6. So to establish some related result, we can prove it here. So this one, this is the problem. So for the conclusion will be here due to some of the question I have recently started to include what are the precise relations between the purely algebraic functionality constructions now. How can we prove these results in the Banach algebra? We have done some work on it also. So to what extent is the derivation compatible with the prime idea of non-commutative rings due to commutative? This is the conclusion. And finally, this is our references. So that will be here. Okay. Thank you very much for.
Thank you, Professor.
If you have any question,
Nice
please.
presentation. If any question is from audience side, they can ask. Any question from audience side? Please type in chat box. Okay, thank you so much, sir.
Thank you.
Now, I would like to request Dr. Nidhi Sharma, our second presenter, from Department of Mathematics and Statistics, MMU, Mullana, India. Her paper title is Impact of Viscosity and Stiffness on Wave Propagation at an Interface. I request Dr. Nidhi Sharma to start her presentation.
Hello.
Dr. Nidhi Sharma.
Hello.
Yes. Yeah.
Hello. Good afternoon. Yes,
good
sir.
Afternoon.
Good afternoon, sir, and good afternoon to all the participants. Sir, can I share my slide?
Sure, ma'am.
Yeah.
Stop.
Sir, is my screen is visible?
Yes, ma'am, it's visible.
Okay. So, so the title of my presentation is the impact of viscosity and stiffness on the propagation, on the wave propagation at the interface. I am here considering an interface problem. That means there are two half spaces. One is the upper one and another one is the below one. So the upper one, I will consider it as the elastic half space, and the below is like the micropolar viscoelastic half space. As you know, the elastic body is one. When a force is applied, the body get deformed, and after the removal of the forces, the body again came to its original configuration. So there are two type of waves exist in the elastic medium. One is the simple SV waves, and another one is the SH wave, and another medium is a micropolar thermoelastic. There are three type of waves are there. That is a longitudinal displacement wave and the set of a couple transverse waves. So according to the firstly, I go for the geometry, so the things become more clearer and easy for me to explain. So this is the geometry of the problem. I consider as already I told that I am considering the interface problem. The medium M dash is considered as the elastic one, and the medium M is like a micropolar viscoelastic medium. So whenever a wave is incident on the interface Z is equal to 0, some waves are reflected in the medium M dash, and only two types of waves are there, and other are transmitted back to the same medium. So the elastic, we can take the example like during like a X-ray. If we consider a human muscle compact bone type, so medium M dash is we can easily understand like a human muscle, and M is like a human compact bone. So these are the waves which we get at the interface. Coming back to the topic, so here we discuss the two type of effects on these waves. First is the viscosity. You know, according to the Hooke's law, whenever the force is applied, whenever stress is applied, it is proportional to the strain. So that means, but when we are considering the effect of viscosity, the stress is rather proportional to the strain. It proportional to the rate of a strain. And what is the stiffness here mean? Whenever a force is applied, the body get deformed. That means the force is proportional to the deformation. So that constant of proportionality is the stiffness. So two types of effects I am going to discuss on this wave propagation. So these are the contents, is the abstract basic equations, formulation of the problem, boundary condition, and the geometry of the problem. Some particular cases are deduced, and graphical representation of the impact of the viscosity and the stiffness, and the use of my problem, and the list of the references. So the abstract, the plane wave propagation at the imperfect interface between the elastic half space and the micropolar viscoelastic half space have been studied. The expression for the reflection and transmission coefficient, which are the ratio of the amplitude of the refractive and transmitted wave to the angle of incident, are obtained. And these some particular cases are obtained for normal force stiffness, transfer force stiffness, and the perfect bonding. The variation of the amplitude ratio with the angle of incidence are shown graphically. It is noticed that the amplitude ratio of the reflected and transmitted waves are affected by the stiffness and the viscosity. Some special cases are also deduced from the present investigation. So here are the, since I am considering the interface problem, so two types of equations I am considering. One is the elastic half space, that is the upper for medium M, and the lower one is a micropolar viscoelastic half space. So following the Erringen 1967, the consecutive relations and the equation of motion in micropolar viscoelastic solid in the absence of body forces and the body couples, equation 1 and 2 represent the relation between the stress and strain, that is simply Hooke's law. and 3 and 4 represent the equation of motion, where u is the displacement and phi is the micro rotation. So since I am considering the effect of viscosity, so all the parameters are proportional to the rate of a strain, and for another half space, that is the elastic half space, the equation of motion is given by 8, and the Hooke's law is presented by the equation 9. So here is the formulation of the problem. We consider a homogeneous isotropic elastic half space and a micropolar viscoelastic half space being in contact with the plane surface, which we designate at z is equal to 0 in a rectangular Cartesian coordinate system. We consider a micropolar viscoelastic plane waves in a xz plane and with the wavefront parallel to the y-axis, and all the variables depend upon x, z, and t, and whatever the deformation along the y-axis, that we considered it as a constant one. So these are the equation 10 and 11 represent the Helmholtz representation. On substituting equation 10 and 11 in the equation number 3 and 4, we obtain the equation 12 to 15. So since we are considering a two-dimensional problem in a xz plane, so the components of the displacement and the micro rotation is given by equation 16 and 17. On eliminating the phi 2, that is a micro rotation, from the consecutive relation, we obtain the equation number 18. Assuming the motion to be time harmonic, since we are considering a wave propagation, so the motion is considered is dependent upon the time. So time harmonic motion is given by equation number 19. So with the help of equation 12, 19 can be reduced to the equation number 20 and equation 21. So we obtain the roots of the equation 20 and 24. We get the two types of equations for the wave propagation. One is the longitudinal displacement wave and other is the CD1 and CD2. In micropolar elastic theory, we have two types of wave. Longitudinal displacement wave mean here the particles move in the direction of wave propagation, and transverse mean the particle move in the direction perpendicular to the wave propagation. So we get a set of two coupled wave and displacement wave. So for elastic half space, again the same we are following the same procedure, that is a two-dimensional case. We obtain the equations for the elastic half space, and this is the geometry of the problem. As I have already discussed, that we are considering z is equal to 0. The waves are incident on the plane z is equal to. We are considering here the interface to be imperfect. I want to explain what is the difference between the perfect and imperfect interface. A perfect interface is one. Usually the traction means the stress and the displacement are continuous over the interface. But we are considering the interface to be imperfect. Here mean the displacement is linearly dependent upon the traction vector. So when the wave is incident on a medium z is equal to 0, making angle theta naught with the z-axis, the two types of waves comes in the medium m dash, and those three types of waves in the medium transmitted in a medium m. So these are the boundary condition. We consider an elastic half space being in contact with a micropolar viscoelastic half space. If the bonding is to be imperfect, the size of spacing between the imperfections are smaller than the wavelength. Then at the interface, these are described by the conditions z is equal to 0, and that is given by a Levering and Rocklin. So since I am considering the effect of the stiffness on these waves, so this the boundary condition first represent the discontinuity along the normal force stiffness. As I have already explained, that stiffness means whenever the stress is applied, the body gets deformed. So Kn is the constant of proportionality, and this constant of proportionality represent the discontinuity along the normal component. Second represent the discontinuity along the tangential component. Third represent the continuity of the normal stress component. This represent the continuity of the stress component along the tangential direction, and this is the micro rotation factor. So these are the different parameters. Q, psi, and phi 2 is given by equation number 35, 36, and 37. So as I have already, these are the mathematical calculations which I have used to obtain the results. That is for the different cases. So these are the amplitude ratios derived for the longitudinal displacement wave and the set of coupled transverse displacement. Some particular cases, as I have told, is derived from these results. That is a normal force stiffness, then transverse force stiffness, perfect bonding, and we have also deduced some special cases. Mean, if we neglect the effect of a viscosity, that is by changing the parameter xi1, xi is equal to lambda, mu, k, and gamma, we obtain the reflection coefficient in the micropolar elastic medium for normal force stiffness, transverse force stiffness, and a perfect bonding. And if we neglect the micropolarity effect, that is by substituting k is equal to 0, we obtain the reflection and transmission coefficient for the elastic and viscoelastic half space. So the another problem can be obtained by changing this in the present problem. So here is the numerical results and discussion. The data for medium m dash we take with the Boolean, and for medium m we have taken from the Erlangen, and we have shown the graphical representation of the amplitude ratio with the angle of incidence. And we can see we have shown here a 4 type of curves are seen in each of the figure. Here we show the effect of the viscosity on the amplitude ratios for the LD wave and CD wave. And this is the utility of the problem. The knowledge of occurrence of waves lead to us to possible to solve the wave response by using the micropolar structure theory, and hence can be referred to understanding the propagation in a biological effect of the human tissue and how simulated waves are propagated in bones such as osteoporosis. We all know that this is a very common problem in a woman after the age of 30. Osteoporosis means there is a gap between the bones due to the deficiency of a calcium. So these type of waves are used to learn in the ultrasonic techniques. Like I have already mentioned in the geometry of the problem that I have considered the medium m as the elastic, and that is behave like a human bone, and the lower medium is like a human compact bone. So this can be this type of a problem can be used in the ultrasonic techniques to know the various type of the biological effects on the human tissue. The research work is supposed to be useful in the further studies, both theoretical and observational, of a wave propagation in more realistic models of micropolar and viscoelastic solid present in the Earth's interior. You know that in the interior of Earth there are many type of ores and minerals are present in inside. So to obtain these type of ores and minerals from the sea level and from the interior of Earth, and to also to know the interior of the Earth, we can use such type of a wave problems, and these are also useful in the geophysical interest, particularly investigation concerned with the earthquake and other phenomena in the seismology. So I would also like to acknowledge one of the very eminent researcher, Professor Rajneesh Kumar Sharma from Kurukshetra University, Kurukshetra, for his valuable suggestion in the work. He has done so many papers, near about 500 paper in the field of the continuum mechanics. You can easily see on the Scopus citation or whatever. So I can take the help of him. So these are the list of the references which I have used in the present study. So this is from my side, and thank you so much for the patiently hearing of my presentation. Thanks a lot and have a nice day.
Thank you so much, ma'am. Your presentation was really very nice, but most of the questions were not clear. It was blurred. So I request while you are preparing your presentation, don't use cut, copy, paste method.
Okay, fine.
By the way, your presentation was nice.
Okay, sir. Thank you so much. Thank you.
Thank you so much. If any question from the audience side, they can ask. Any question? Okay, let me call our third presenter, ID number 03, Mr. Hayum Muleta Chemeda. Assistant Professor in the Department of Mathematics, Jimma University, Ethiopia. His presentation title is Difference Scheme combined with Richardson Extrapolation for Fisher's Equation. I request Mr. Hello, please share your presentation.
Okay, thank you very much for just inviting me. Is my slides visible?
No.
Let me share this. What about now? Hello?
Yeah, it's visible.
Okay. Thank you very much. Okay. Okay.
Mr. Abebe, mute yourself, please.
Okay. So the title of my presentation is Compact Final Difference Scheme combined with Richardson Extrapolation for Fisher Equation. So these are some of the outline of the presentation. It starts with that of introduction and the ends with the conclusion. So when we come to that of the introduction, the one-dimensional Fisher equation is given by this equation 1, together with that of the initial condition in equation 2, and that of the boundary condition in equation 3. And these f of x, g1 of x, g2 of x, t are assumed to be continuous and sufficiently continuous. And this is a nonlinear because of this term. And this is what we call one-dimensional Fisher equation. And these are some of the applications of this Fisher equation, and that may be used as a model for the spatial and the temporal propagation of a variable gene in an infinite medium. And the evolution of neutral population in a neutron-free reactor, and the rate of advance of a new advantageous gene with a population of a constant density. These are some of the applications where this one-dimensional Fisher equation is going to be applied. And these equations is simply the domain discretization is the direction of the spatial domain, and that of in the temporal direction. So we will have such kind of discretization. And when we come to that of the mathematical formulation and the that of analysis, here we get that the fourth order compact scheme. Using the Taylor series expansion, we will have the second and the first derivative of u with using equation 4 and 5. And these one are the central finite difference approximation for the first and the second derivation. Whenever we just substitute equation 5 into equation 1, we will get this equation 7. Again, and when we just differentiating the original equation twice with respect to x and rearranging, we obtain this equation 8, you know. So replacing the first and the second term of u that we have obtained in the previous equation into equation 8 from 4 and 5 respectively, we get this equation 9. So instead of this expression and this expression, if we replace them with their corresponding finite difference approximations, we'll get this equation 9, equation number 9. So now when we substitute equation 9 into equation 7, and after some rearrangement and simplification, we'll get this equation number 10, equation number 10. So that in this equation number 10, we do have some nonlinear terms, and this is one linear term, nonlinear term because of this square, and we have also another nonlinear term because of u here in the multiple, and we do have also here the nonlinear terms. So before just discretizing using the Crank-Nicholson scheme, we need to non-linearize these terms using the method called the lagging method. So just after this lagging method works at the ji's, the j's and the j plus 1's position, and then after discretizing it, after linearizing that, when we just discretize using the Crank-Nicholson discretization scheme, we will get equation number 11. So that after simplification, after a very long and simplification and rearrangement, we'll get equation number 12. So equation number 12 is said to be the fourth order compact Crank-Nicholson scheme for solving the one-dimensional Fisher equation. We do have the coefficients AI, BI, CI, and the DI is constant. So these AI, BI, CI, and the DI are also given by this one. And this is the developed scheme. Next, I'm going to just deal with the stability analysis of this one. to show the stability analysis of this, I'm going to use the von Newman stability method. So to do so, I'm going to have the linear term of this equation, the number 11, so that having this for this a constant, we also have to have a certain constant here to make it linearized. So to avoid the use of I and the j in complex number, I'm going to replace this by this in equation 13. And after some long but straightforward simplifications, we obtain equation number 14. Equation number 14. So that replacing this term, you are nm by this one, and the solving for this side, at the end of the day, we will get this one, the absolute value. And this, when we look at this, for instance, when we simplify with this one, it will be 2 cos theta, and this we take the absolute value, and this is for sure it is less than or equal to 1, because since 0 is less than or equal to absolute value of cos theta, and this is less than or equal to 1, and the magnitude of this is always less than 1 for every value of r greater than 0, so that this equation number 12 is unconditionally stable for every value of r greater than or equal to 0. And the next one is the application of the Richardson extrapolation. The purpose of this application of the extrapolation is to increase the accuracy and as well as to accelerate the rate of convergence of this. And the aim is here, how to apply the Richardson extrapolation is to apply the difference scheme on 2 consecutive grids, one coarser and the other is finer, in order to obtain the solution to the higher order approximation of this one. So here is how it works. Consider 2 consecutive grids on this, and this is coarser, and this is when h is halved, and this is finer. Assume also this equation number 15 and the 16 are also valid for solving this equation number 1 that we have seen at the very beginning. The aim is to eliminate this term, ch the power of 4 and the ch the power of 4 over 16. So to do so, and these are h of k and r h over 2k are of order 6 in the direction of the spatial direction, and that of the second order in terms of the temporal direction. So to eliminate these, I have to multiply equation number 15 by minus 1 over 15, and I have to multiply this equation 16 by 16 over 15. And then when I combine it, I eliminate and I get equation number 16, just like this. So that this is 6th order in the direction of the spatial direction, and that of second order in the direction of the temporal direction. So this is what we call the Richardson extrapolation variant of equation number 12. Next, I'm going to just validate this proposed method using some numerical examples. So to validate this, 2 numerical examples are presented, and these 2 numerical examples do have their own exact solution. And this is pointwise absolute error, and this is L infinity or maximum norm, and this is what we call L2. So example 1 is consider equation 1 as considered in this reference with beta is equal to 1 and alpha is 6, in that where the domain is 0, 1. For this equation, the initial condition is this one, and the boundary conditions are this one. For this particular equation, we do have the exact solution is also given by this one. Again, we do have another example too, where x is in this domain with boundary conditions. As x goes to minus infinity, u of xt is 1, and as x goes to that of positive infinity, u of xt is 0. And the initial condition for this particular example is given by this expression, and the exact solution is this one. Now, this table 1 is the comparison between pointwise error for example 1, where change of t is this. No? Where change of t is this one for this, and when we compare the result, here I compare the result with the previous published article by 15, modified by Taylor box method and the present method. When we see the results, our method just better approximates this equation. So here it is 5, 6 on this one, and that is 6. Somewhere it is also 7 here. We do have 6, and when we look at this, it is 0 to that to minus 5. So from this, we can conclude that it better approximates this equation problem. And when we compare L2 and the L infinity norms for this, it's just the present method approximates the problem very nicely, as t from t is 5 over long range of time, we'll have up to 10 raised to minus 15 here, L infinity 10 raised to minus 14, and blah blah. So it approximates the exact solution very well. So this is the comparison of the exact solution and that of the approximate solution. So as you can see from this graph, both the exact solution and that of the approximate solution overlaps to verify that the approximate solution approximates the exact solution very well. And this is also the 3D version of it. And here also, there is no difference between the two. So there is the exact solution and the approximate solution are in a good agreement. And when we come to that of the second example, comparison of the L2 norm for example 2 is this one. Again, it is up to 10 raised to minus 16. It approximates the exact solution very well. So the method is so outstanding. And this is what we call numerical and exact solution of example 1, when h is equal to this 0.1 and the change of t is this one. There is no difference between the exact solution and that of the approximate solution. As from the very beginning, as x goes to positive infinity, the u of x goes to 0, it says. So you can see from this graph, it goes to 0. As x goes to infinity, it goes to 0. As x goes to minus infinity, it is 1, says. So here it is 1. So the equation, the given example and the graph also agree. And when here is also another comparison with method in 29 and our present method, L1 error, L2, L infinity. So in this, our method just outperforms the method in 29. At this, for instance, our is 10 raised to minus 2, it is 10 raised to minus 1 here. As we go down, our is just the error is also get minimized. And here it also the previous result going to just starts to diverge, whereas ours is going to decrease. And when we come to at this point, it diverges. The result of the previous result diverges. In our case, it is 10 raised to minus 2. As we go down, our is just the error is going to be minimized. And as we go down, the error in the previous paper going to divert. So from this, you can also understand that our method better approximates the one-dimensional Fisher equation better than the other methods. And this is also the three-dimensional. From this, as x goes to minus infinity, it goes to 0. So here it is 0, And in between from this, and this is the replica, So this part, we have three parts. As x goes to positive infinity, it is 0. As x goes to minus infinity, it is 1. And between that, it is this. So, and this part is 0. And we have this part. Somewhere it is going to be 1. So there is also the graphical agreement between the exact solution and that of the approximate solution. And as we have seen in tables also, here is the conclusion. In this paper, fourth order compact Frank-Nicolson scheme combined with the Cartesian interpolation for solving the one-dimensional Fisher equation is presented. First, the derivative involving the space variable is discretized by fourth order compact partial difference method. Then the nonlinear term in the governing equation is linearized by the lagging method, and the derivatives involving the temporal variable is discretized by the Frank-Nicolson scheme set. The method is found to be unconditionally stable, as I've shown that, and the fourth order accurate in the direction of the space variable, and the second order accurate in the direction of the temporal variable. When combined with the Richardson extrapolation, as shown in equation number 17, the order of the method is improved from 4 to 6 order in the direction of the space variable. And that is, so to validate the applicability of the present method, we have considered two numerical examples, and the results are presented in terms of tables and that of graphs. From the results displayed in tables and the graphs, we can conclude that the present method is efficient, as you have seen the results, and it's also very much accurate, better approximate the one-dimensional Fisher equation than some of the methods presented in the literature, as I've shown you. So these are some of the references. And thank you for your attention. If you do have questions, you're welcome.
Thank you so much, Mr. Haile. I have some questions for you. What are the conditionally stable solutions and unconditionally stable solutions?
Yes.
What is the difference between conditional stable solutions and unconditionally stable solutions?
Okay, we say that the numerical method is said to be conditionally stable if it is stable for some value of r. For instance, my r here is beta times k over h square. So if it converges for some value of r and diverges for some value of r, we say it is conditionally stable. If it is just stable or converges for every value of r, beta times k over h square, we say it is unconditionally stable. There is no restriction of r that way.
Okay. And you said there is no difference between exact and approximate solution. So why are you using the term approximate solution if there is no difference?
Yes, pardon once, please. You know, when we say there is no difference, it doesn't mean that exactly there is no difference. Yes.
In your presentation, you used a sentence, there is no difference between exact and approximate solutions. If there is no difference or no error, so why are you using the term approximate solution? Why not exact solution?
Okay, thank you for your nice question. Actually, when I say there is no difference between, I'm talking about the graph. You know, the graphs overlap that way. But there is a difference, even if the difference is there, but the difference is very small. It is up to 10 raised to minus 16, up to 10 raised to minus 4, and the like. There is a difference, but when we see from the graph, there is an overlap. That means the approximate solution better just agrees with the exact solution. It doesn't mean that there is no difference between the exact solution and that of difference at the approximate solution.
So numerically, there is some error. So the next question is it possible to extend your method to sixth order?
Yes, yes.
Is it possible to extend your method to sixth order?
Sixth order?
Yes.
Yes, using the Richardson extrapolation as a technique, I extended to that of the method to sixth order in the direction of the x-axis. Without using that of the Richardson extrapolation, it is possible to extend it to the sixth order. But due to the case of the existence of the non-linearity, it may be tedious, but it is possible. It's possible.
Okay, thank you so much, sir.
Thank you
now,
for having me.
Next presenter is Dr. Hazel Yuskeskia, a research scholar from Department of Applied Mathematics, Dicle University, Turkey. The paper title is Non-Existence of Global Solutions for a Delayed Wave Equation. Dr. Hazel, am I audible?
Yes, I am here. Yes, okay,
yeah.
Professor.
Please share your
And now I will share my presentation, please.
Sure. Participants are requested to mute them.
Now, is it visible? Is it visible, my presentation, or not?
Yes, ma'am, it's visible.
Okay. Hi, everyone, again. I am Hazal Yüksekkaya. I'm PhD student. I will talk about the non-existence of global solutions for a delayed wave equation. In this work, we investigate the following logarithmic M Laplacian type equations with delay term. As you see in the equations, we have M Laplacian term, one delay term and logarithmic source term with initial and boundary conditions. Here, omega is a bounded domain with a sufficiently smooth boundary. And also we have these conditions here. P is greater than M and it's greater or equals to 2. K and mu1 are positive constants. Mu2 is a real number. Also, we can say there is a time delay. And this is our M Laplacian term. The functions U0, U1, and F0 are the initial data. Firstly, I want to talk about the problems with logarithmic nonlinearity. As we know, the logarithmic nonlinearity generally appears in supersymmetric field theories and cosmological inflations. Also, we can see that these terms with nuclear physics, inflations, cosmology, geophysics, and optics. When we look to literature, firstly, we can talk about the works of Virula and Myskielski in 1975 and 1976. Firstly, they investigated the following equations with logarithmic term, as you see here in the equation 2. This equation is a relativistic version of logarithmic quantum mechanics, and they are the pioneer of this kind of problems. And then in 1980s, Kazaneva and Horrocks introduced the following logarithmic equations, and they proved the existence and uniqueness of the solutions for this problem. And also in my problem, I have a time delay. So I will talk about the problems with time delay. As we know, time delay appears in many practical problems, such as thermal, biological, chemical, physical, and economy. And we can say that the delay effects may lead to instability. A small delay may destabilize a system which is uniformly asymptotically stable in the absence of delay, unless control terms or additional conditions. In 1986, Datko indicated that a small delay in a boundary control is a source of instability. And Nikkei and Painotti investigated the following wave equations, these equations 4, with linear damping and delay term. They proved the stability for these equations. And Kafini and Mesudi treated the following equations with delay. We can say that Kafini and Mesudi studied this equation 6, and they proved the blow-up of solutions. Firstly, I will talk about some lemma and notations, and then I will talk the proof of blow-up of solutions. Blow-up of solutions is, we can say that it is the non-existence of global solutions also. Firstly, similar to the work of Nikkei, we can introduce the new variable. Thus, we can get this equality. And when we put into our equations, then our problems can be transformed in that form. This is our new problems, as you see here in 7. Firstly, we should define the energy functional of this system. This is when we calculate it, we can get this energy functional, and also we have these conditions 9. We can say that the energy of the problem is non-increasing under these conditions. And firstly, I should give some lemmas. The first lemma shows that the derivative of energy functional is less than this value, so it is non-increasing. This is the proof of our lemma. When we multiply our equations, the first equations by UT and integrating over domain, multiplying the second equations by this value, and when we integrate, so we can get the derivative of energy functionals, it satisfies this equality 11. Also here we use some inequalities like Young. Thanks to Young inequality, we have this estimate here, and then when we can see that the energy functionals is less than this value, and this the inequality of 12 is satisfies. So when we choose the coefficients like C0, we can see that the energy functional is non-increasing. The second lemma that we will use later is also about the logarithmic source term. So this inequality is satisfies. Also, we have the proof of it. That's similar to the work of Mesudi. And also here, this lemma, we can see that the norm of u square is less than the integral of logarithmic source terms over 2 divided by p and plus nabla u over 4 divided by p. And also we can say that the integral of logarithmic is positive. And also in this lemma, we can see that the norm of u over s is less than the norm of u over p, and the norm of nabla u over m. For our we are going to prove the non-existence of global solutions or the blob of solutions. The blob of solutions is a mathematical behavior of solutions. We can't calculate the direct solutions, just mathematical behavior for blob. Firstly, we should define an HD functional. It is a minus energy functional, as you see here. And this is our theorem, the main theorem. So under these conditions, we can see that the initial energy functional is non-increasing. It's less than 0. So the solutions of our problems will blows up in a finite time. And this is our proof, as we see that the energy functional is non-increasing. So we take the derivative of HD functionals, and we can see that the inequalities of 17 is satisfies. Then we can introduce an LT functional. It is related to our HD functional, of course, the energy functionals. So we can see that this is the boundary of alpha. And when we took the derivative of LT functionals, we can get this in this equality 19. And also here we should get some estimates. For this we use some inequalities like Holder in Young or other ones, and we can see that this estimate of 20 is satisfied. When we put it in our equations, we can see that the derivative of LT functional is greater than the sum of these terms. And here we choose this equality, and when we rearranged, we can see that the derivative of LT functionals satisfies these inequalities. Also here, for an A from 0 to 1, we can see that the inequalities of 22 is satisfies. And also from 13, the number of equations 17 and Young's inequalities, we can see that h over alpha multiplied by the norm of u square is less than this, the sum up of this value. And by some calculations, we can get these two conditions. And from lemma 2 provides these inequalities of 23, as you see here. And when we combine 23 and the equations of 22 and 23, we can get the derivative of LT functional is greater than the sum up of this value. And also here, we should choose our coefficients positive, as you see here. And we choose K so large, and we choose these coefficients enough positive. And then we can get the derivative of LT functions is greater than the sum up of these all terms, 25. And we can see from Holder inequalities these estimates, we can get these estimates 27. And also by lemma 4, we can get the estimate 28. And when we now we should calculate the L over 1 divided by 1 minus alpha, and we can see that it is less than the inequalities 29. And when we combine 25 and 29, we can obtain that the derivative of LT is greater than L over 1 divided by 1 minus alpha. And here we make a simple integrations over 30, and we can see that the L over alpha divided by 1 minus alpha is greater than 1 divided by this value. And LT blows up in time. T star is the upper bound of blow up of time. So this is the upper bound of this delay, this time. So we can see that the solution of problems blows up in a finite time t, and this is our references. Thank you very much for listening.
Thank you so much, ma'am, for your nice presentation. I have two questions for you. Can you give a real example of time delay problem? And what do you mean by asymptotic stable?
For a delay term?
Can you give a real example of time delay problem?
Yes. For example, we can you ask me about a delay term? Yes.
I'm asking about a real example of time delay problem.
Okay. For example, one of for wave equations, normally when we get the blow-up of solutions, we have a t time, but when we make a behavior, it can be an short time from this time, not the real time, another short.
For example?
It can be, there are a lots of like wave equations,
wave equations.
or water wave equations. There are lots of.
Can you say Schrodinger wave equation is time delay problem? Is it related with time delay problem?
Sorry?
Schrodinger wave equation. Okay, leave it. Can you please explain what are asymptotically stable solutions?
Asymptotically stable?
Yeah.
Normally, for our problems, normally we have this delay term. When we make some conditions, we can make it more stable. These conditions can be initial or boundary conditions, or another conditions that extra we add.
Okay, thank you so much, ma'am, for your nice presentation.
Okay, thank you.
Our next presenter is paper ID 05, Mrs. Vanashri Gupta, a research scholar from Interdisciplinary School of Scientific Computing, Savitribai Phule University, Pune, Maharashtra, India. Her paper title is A New Approach to Construct K and Threshold Secret Sharing Schemes Based on Finite Field Extension. Mrs. Vanashri Gupta, am I audible?
Yes, greetings of the day to everyone.
Thank you so
Let
much.
me share my presentation.
Yeah, sure, ma'am.
Is it visible?
It's processing, ma'am.
Okay, till that time I'll give the introduction. Nowadays we are connected with network. So whenever network will be there, there is a big concern related to security. So whenever we are sharing something, some data or some password or some keys to another person, the security is a big concern. So suppose I want to suppose we are having a bank locker and we are going to open our wallet. So usually two keys are associated with it. One the locker person is having, and the other is a authority person of the bank. So if both the key matches, then only the locker will be opened. So the same concept is applied over here. A threshold secret sharing is a scheme in which a secret. So the example which I have given is a wallet. Wallet is a secret, and the shares are the keys. So the keys are divided among two persons. So same concept is applied over here. The secret is divided into n number of shares, and out of n number of shares, if k number of people come together, then only we can recover our secret back. So this is usually applicable in passwords, missile launching and other places also. So in the literature, there are a lot of threshold secret sharing methods available. Mainly 4 secret sharing methods are available. One is Shamir secret sharing, other is blacklist secret sharing, third is Asmith-Bloom, and the Chinese remainder based method. So all of these methods are having some pros and cons. So out of which we are considering blacklist method, and we are trying to improve it using Galois field. We are trying to apply.
ब्लश कर रहे हो वहां बैठ के क्या वो दीक्षा और वो भी कर रहा हूं
I request to all kindly mute yourself.
So firstly, I'll give the overview of blacklist scheme. Blacklist scheme is a geometrical approach in which the secret is nothing but a point in a t-dimensional space in which we are considering that each layer is a hyperplane, and if all 10 different hyperplanes meet together, then only the intersection point is our secret. So for that, we are considering a linear system of equations and we are solving them. So for that, algorithm is already there. That is, we have to pick time, we have to create a secret, and we have to create different points according to that, and we have to consider those equations and solve the system of linear equations. So the intersection point is nothing but our secret. So these are 5 equations given, and I'm considering out of 5, if 3 equations or 3 shares come together, then only I can recover the secret. So these 3 equations are there, and out of 3, I'm considering first 3 are coming together, which are having coefficients a1, a2, a3, b1, b2, b3, and I'm solving them, and the meeting point will give me the secret. So similarly, an example is considered. In this, 4 equations are given, out of which 3 equations I'm considering 4, 52, 36, 19, 27, 65, and the constants are 68, 10, and 18. I'm solving them, and you can use any method, Gaussian elimination, variable elimination, you can solve it, and the intersection point is the secret. Now this is the method, but it is having a lot of drawbacks. I'll explain the drawbacks at the end. I'll explain the how we are going to do improvement, and what will be the improvement, that also I'll explain at the end. So same thing is applied, same concept is same, but here we are considering the field extension. So in this we are considering MQ is the space, and in this I'm considering a Galois field or finite field, and I'm transforming it to the polynomials. So the algorithm will be whatever input is there that is in the normal field, and that is transformed into the Galois field. So the U vector, which is our input vector, that is transformed to the Galois field vector with respect to the given base, whatever base you are considering, and all the vectors are written in the polynomial form. So how to convert, that example is also given. Suppose 7 is my input, and I'm considering the space is M8 space, so that is converted first to the binary form, that is 111 is the binary form, and then it is transformed to the Galois field, that is GF8 field. And in Galois field, theta will always be a primitive element. And one more example is given. I am considering 5 as an element. For that, I am considering M9 as the space, and 5 is converted to the GF9 space. Again, theta is the primitive element. Now, whatever the input is there, that is converted to Galois field. Now, for recovering our secret back, again, we since now for the second thing, whatever input we are having, that is in the Galois field, but our actual input is in the normal space. So I want to recover it back. So again, second algorithm is there, how to recover from Galois back to the normal space. So that algorithm is whatever the operand polynomial is there, that we have to transform to integers back. So again, now the input will be in Galois field, and we want our output in the normal form. So now the reverse process will be applied over here, and our proposed algorithm using this blacklist is we are considering same vector in integer form, whatever the coordinates are there, which I'm considering first coordinate as my secret, and the n vector now they are distributed among n number of participants. So now I'll get the shares as AU1, AU2, AU3 and up to AUN, and all of them I'm considering its secret pieces I'm calculating, and then I'm transforming it to the Galois field. And this is first phase, that is secret distribution, and then the secret recovery phase will come. In that, whatever the participants are there, they are sharing their shares, and out of which I am recovering back my secret. So for that I have to solve the system of linear equations. So example is considered. We are considering an irreducible polynomial of degree 3, since I am considering the F2 as my space. So the equation is x cube plus x square plus 1, and since it is F8 space, so 8 participants will be there, and out of which that is 0, 1, theta, theta 1, theta square plus 1, theta square plus theta square plus theta plus 1. And I am considering for my secret sharing, I am considering n number of participants as 5, and out of which 3 can recover the secret, and my secret is 4. Now all these are transformed. Now transformation from integer to the Galois will be 0 to 0, 1 to 1, 2 to theta. This is given in any literature. Now I'm considering the vector space. My vectors are, first vector is 0, 2, 2, second is 1, 3, 3. Since I'm considering 3 participants out of 5 participants, so it is given, and 5 vectors are given, out of which now I'm considering first I'm transforming all those to the Galois field, and out of this I'm considering we can recover. So the recovery is through second, fourth and fifth. This transformation is done according to the algorithm which I have explained. So now for recovery I'm considering 2, 4 and 5 are coming together. So 2 is having coefficients as 1, theta 1, theta plus 1 and theta plus 1. So that is transformed, and I have solved it, and whenever we are solving, we are getting it in Galois field. That is again transformed back to the integers, and we will recover the vector, that is 5, 2, 3. And as I said earlier, the first element of the vector will be our secret. So 5 is our secret. Now, what is the security analysis of this? Since we have splitted the secret into n number of shares, and while reconstructing we are considering the k number of pieces to collect together. So this is done in terms of extension field. The extension field will give the security and reliability, since there is no shadow available of any share. Now this is the comparison done with the already existing schemes and our proposed scheme. So suppose we are considering the Shamir's sharing scheme. Shamir's sharing scheme is having is using polynomial interpolation. It is a perfect scheme. It is ideal scheme. Perfect in the sense that the security, whatever security we are expecting, that till that security we are reaching, and the number of the share size is equal to the secret size. That's why it is ideal also. These methods are not providing multiple secret sharing scheme at a time. Only one secret is shared at a time. These are threshold method. None of them is verifiable nor proactive, and all of them are having lower security. But our proposed system is having higher security compared to all of them. The conclusion is, we have proposed a new threshold secret sharing over finite field extension using Blackley secret sharings as a base. And due to the finite field, the security of the system is increased. This system is very reliable, and this system is based for black layers, but if we consider the same method, like whatever the integers are there that are transformed to Galois field, and then the processing is done based on the method which we require, like we have considered black layers as a base, we can consider Shamirs as a base, and again we can apply the reverse process, and we can do the we can recover back our secret. So this method can be applied to any other method as a base, like Shamirs we can consider as a base, and this method is having a lot of application, like image secret sharing. In image secret sharing, suppose image is considered as a secret, and the image is divided into n number of pieces, and the pieces, whenever you are considering a single piece, it is a noise, but whenever the images are overlapped to each other, you can recover back your original secret. So this method can be applied over there. So this could be a application, and this can be used in steganography. These are the references. Thank you, and I am open for questions.
Thank you so much, ma'am, for your nice presentation. One question is for you, ma'am.
Okay.
Can you please elaborate the term secret recovery?
Yes. See, general example I am giving. Suppose 4 friends are there, and they are moving somewhere, and in between they got some treasure, and now they don't trust each other, and then how to divide the secret? So what? And they're having map to the treasure. So what they will do? Whatever the map they are having, they will divide that map into 4 pieces. They will tear that map, and they will divide each piece to 4 of them. And whenever the 4 pieces come together, that time only we can get the map back. So this is the general example. So in this, this is a threshold secret sharing method of 4 out of 4. That means the secret is divided into 4 pieces, and if all of the 4 pieces come together, then only they can recover the secret back. One more example I'll give. Suppose a missile launch is there. In a missile launch, usually what is happening in a suppose a company is there who is doing missile launch. So there are n number of people involved in the missile launch. Some are senior people, some are middle level, some are junior persons also. So what usually they will do, they will not give all the authority to higher person, or all the authority to middleman, or all the authority to the junior person. What they will do, they will consider few people from higher grade, few from middle, and some from junior grade. So suppose higher grade ka 5 people are involved in the technique, and out of which only 1 is sufficient, out of middleman 1 is sufficient, and out of junior 1 is sufficient. And if these 3 people come together, then only the launching will be happen. Otherwise anyone can launch the missile. So that thing should not happen. That's why this is used. And I already gave an example of locker system. In locker, whenever we are opening any locker, so one key the bank person will give to us, and one he will keep with him. And whenever we are want to open again, like I have kept some secret in that locker, and few days after I again met to the bank. So what I have to do? I have to put my key. The bank person will put his key. If both the key matches, then only the locker will be opened. But suppose instead of I, some other person went over there, and he is having some key. But whenever he put his key, and the bank person will put his key, if both keys will not match, because he is not an authorized person, and the key is not matching. If the key is not matching, locker will not open. So this is the main idea behind this.
Thank you so much for your nice explanation, ma'am. Thank you so much.
Okay. Any more question?
No, ma'am. Thank you so much.
Okay. Thank you. Thank you for listening.
Thank you. Our next presenter is paper ID 06, Ms. M. Vijatha. She is a research scholar in the Department of Mathematics, VIT Vellore, India. Her paper presentation title is Entropy Optimization on MHD Non-Newtonian Hybrid Nanofluid over a Stretching Cylinder with Radiation and Titanium-Christov Heat Flux Model. Ma'am, are you available?
Yes, sir. Yes,
Okay.
sir. Is it visible, sir? Can I share my presentation?
Sure, ma'am.
Is it visible or not, sir?
Yes, ma'am, it's visible.
Good morning to one and all. I am Vijata, internal full-time scholar doing PhD under the guidance of Dr. P. Bala Ankireddy, sir, Assistant Professor, Department of Mathematics, School of Advanced Sciences, Vellore Institute of Technology, Vellore. Title of this presentation, Entropy Optimization on MHD nanofluid, non-Newtonian hybrid nanofluid over a stretching cylinder, radiation and Cateno-Christo heat flux. In this topic, magnetohydrodynamic boundary layer phenomena of non-Newtonian hybrid nanofluid following on a stretching cylinder surface. In this, we have taken ethylene glycol and water as the base fluid and CuAl2O3 as the nanoparticles in critical for heat exchangers, fiber coating and transportations among other applications. There are numerous theoretical models available now for depicting the thermal transfer impact of non-Newtonian liquids follows over a cylinder. Additionally, an external magnetic force is ideal for addressing the physical properties of the fluids and regulating the type of heat and momentum transfer in the system, taking this into consideration. We explored the heat transfer behavior of two separate non-Newtonian MHD fluids when a cylinder is stretched with heat generation employing a new heat flux theory provided by Cateno-Christo heat flux. The fundamental of partial differential equations are transformed into ordinary differential equations using the appropriate similarity transformation. Those ordinary differential equations are solved using the fourth order Runge-Kutta shooting system. Homotopy perturbation method for the nonlinear system is developed for the comparison purpose, and more accurate and reliable outcomes is illustrated throughout graphs and tables. It is observed that the fluid velocity reduces for the higher values of magnetic field. Higher values of the heat generation parameter improve the temperature profile. Nusselt number dimensionless when developing the Brinkmann number and Eckert number. Thermal relaxation effectively augments the Bejan factor in the flow of Williamson fluid more than it is does in the flow of Kazan fluid. In this figure 1 shows the geometry of the problem. Here U and V are the velocity components along x and r direction. Here UW is the wall velocity, TW is the wall temperature. By considering this assumption, we framing the Gowning equations. Thermophysical properties of this paper, ethylene glycol and water as the base fluids, Al2O3 and Cu as the nanoparticles, which is the presented in the Gowning equations. This equation represents the continuity equation. This equation represents the momentum equation. This equation represents the energy equation. In this momentum equation, this term represents the Kazan fluid. This term represents the Williamson fluid. This term represents the Cateno-Christo heat flux. This term represents the heat generation. This term represents the radiation. This term represents the magnetohydrodynamics. The corresponding boundary conditions are as follows. Here VW represents the VW equal to minus A by R into root of mu B by L into S. So the Gowning partial differential equations into set of coupled nonlinear ordinary differential equations. We now introduce the following similarity transformations. The equation 6 automatically, that means continuity equation automatically satisfies. The equation 2 and 4 transformed into the following equations. The transformed boundary conditions. In these non-dimensional quantities, here This term represents the curvature parameter. This term represents the magnetic field. This term represents the Prandtl number. This term represents the Eckert number. This term represents the radiation. This term represents the thermal relaxation parameter. This term represents the heat generation. This term represents the Wissenberg number. This term represents the section injection parameter. This term represents the stretching and sinking parameter. This term represents the Brinkmann number. In terms of biomedical, industrial, and scientific applications, the physical quantities of the consider are the spin friction coefficient and the heat transfer coefficient. Here, surface shear stress, this term represents surface shear stress, and this term represents the local Reynolds number Rex equal to XUW by mu. Non-dimensional spin friction coefficient, this term represents, and heat transfer rates, this term represents. That means Nusselt number. Entropy generation. The dimensional form of entropy generation is presented in equation 14. In this entropy generation consists of 4 irreversibility process. In that 4 irreversibility process, this term represents the thermal irreversibility process. This term represents the Kazan and Williamson irreversibility process. This term represents the magnetic field irreversibility process. In equation 15 represents the non-dimensionalness of entropy generation. Here Ng is the local entropy generation, alpha 1 is the dimensionless ratio variable, and Br is the Brinkmann number, and Be is the Bejan number. Here Be equal to entropy generation due to heat transfer total entropy by total entropy generation. In this paper, we use numerical procedure. The RK fourth order method and the shooting procedure are used to address the coupled nonlinear ordinary differential conditions, equation 7 and 8, and the boundary conditions, equation 9. The following process is used to convert the arrangement of coupled nonlinear ordinary differential equations into account of the first order differential equations. This is the process. And HPM, that means homotopy perturbation formulation. This is boundary conditions. And comparison for the various Prandtl number parameters at the previous results and the present results. Result and discussion. Figure 2 shows the Kazan fluid comparison between the numerical method and the HPM method for velocity. Figure 3 represents the Williamson fluid comparison between the numerical method and the HPM procedure for the velocity. Figure 4, Kazan fluid and comparison between the numerical and the HPM procedure for the temperature profile. Figure 5 shows the Williamson fluid comparison between the numerical method and the HPM procedure from the temperature profile. Here, figure 6 shows the influence of magnetic field on velocity. When increasing the magnetic parameter decreases the velocity. Physically, the increasing the magnetic parameters initially generate the Lorentz force. Figure 7 shows the influence of radiation on the temperature. Physically, the influence of the radiation improves the thermal diffusivity of the medium, so it is increases. Figure 8 shows the influence of magnetic parameter on the temperature profile. And figure 9 shows the influence of the heat generation on the temperature profile. Influence of the Brinkmann number on Ng. Figure 10 shows the influence of Brinkmann number on the entropy generation. When increasing the Brinkmann number increases the entropy generation. Physically, it is related with the heat condition from the surface to the fluid. More heat transformed to the fluid on the entropy generation is increases. Figure 11 shows the influence of Brinkmann number on the Bejan number. When increasing the Brinkmann number decreases the Bejan number. Figure 12 shows the influence of pi 1 and the magnetic field on Nusselt number. Figure 13 shows the influence of volume friction phi 1 and the magnetic field on spin friction coefficient. Conclusion of this presentation. In this article, we analyze the comparative analysis on magnetohydrodynamic and Kazan-Williamson hybrid nanofluid flow over a stretching cylinder, along with the Catano-Christo heat flux model. The Runge-Kutta fourth order shooting system is used to solve those ordinary differential equations and the homotopy perturbation method for the nonlinear system of developed for the comparison purpose, and more accurate and reliable outcomes are represented via graphs and tables. This type of theoretical examination is utilized in the nanotechnology and industrial areas. In particularly, ethylene glycol and water as the base fluid, CO and Al2O3 nanoparticles are used in solar thermal systems, solar heat exchangers, and solar electrical power generations, etc. The major outcomes of this study is the boundary layers in velocity profiles as Kazan and Williamson parameters of the magnetic field are improved. The thickness of the thermal boundary layers and heat transfer rates increased due to increasing the magnetic field and radiation parameters. When the heat flux parameter is present, the Kazan fluid more influenced than the Williamson fluid. Thermal relaxation has the tendency of the velocity and temperature curves. Nusselt number decreases when developing Brinkman number and the Eckert number data. References. Thank you.
Thank you, Ms. Vijata, for your nice presentation. Ma'am, we have some questions for you.
Okay, sir.
Ma'am, what are the Brinkman numbers and local Reynolds number?
Sir?
What are Brinkman numbers and local Reynolds number?
Brinkman number.
You have used these terms.
Yes, sir, but I forgot it. So,
okay. You have used fourth order Runge-Kutta method.
Yes,
but
sir.
now it is researchers are using seventh order, eighth order. Why you have used this method?
Sir?
By the way, yes, ma'am.
Sir, now I am doing Runge-Kutta fourth method. In future, I can definitely learn and Runge-Kutta seventh order.
Okay. Thank you so much, ma'am.
Thank you, sir.
Welcome.
One question.
Okay, one more question, ma'am.
Thank you. Thank you for your presentation. I do have one question. You know you are doing numerical solutions. You obtained numerical solutions. So when we develop some numerical method, before just validating the method with some numerical examples, it is better to do the analysis, that of stability analysis, consistency, and that of convergence. Have you done this analysis?
Sorry, sir, I couldn't understood.
When we develop certain numerical methods, before applying those numerical methods, it is better if we do analysis. The consistency of the numerical method, the convergence, and that of the stability of the numerical method. I didn't see any kind of analysis in your presentation. So have you done, or you are intending to do in the future?
Sorry, sir?
Ma'am, I would like to elaborate. Have you checked the consistency and convergency of the method you applied in your research?
Yes, sir.
Including the stability.
So what you got?
Same accurate results I got, sir. Accurate and reliable results.
Okay,
I
thank you so much.
understood. Okay,
look,
sir,
listen, please.
Okay, sir.
Look.
Okay, sir.
We can say that the obtained solution is accurate, reliable, and the like. If you check the convergence, the consistency, and the that of the stability. If you check, for instance, the consistency and the that of the stability, by Laplace's equivalency theorem, the convergence is going to be guaranteed. But you didn't check the consistency and the that of the stability. How can you say so your solution is accurate and reliable?
Oh, I can go through it, sir.
Please let you just think for the future, okay?
Oh, okay, sir. Okay, sir. Definitely I can. Okay, sir.
Any other question from audience side?
I have
Any
one
other?
question.
Okay.
Thank you, dear madam, for your nice presentations. What
Okay,
about
sir.
the validity performance of your model?
Sir?
Can you justify about your model performance, validity performance for your model?
Sir, it's better to type your question in chat box so that he can understand better.
What about the performance of validity for your model?
Applications of my paper, sir. I didn't understood, sir. Sorry, I didn't understood your question.
Okay, I want to ask what about the validity performance for your model? You model some problems, but what about the validity? Whether your model is valid or invalid? What about
Valid,
its
sir.
performance?
Valid.
I will check that. How can you say that it's valid? Have
It is
you checked
better
it?
to justify. It is
I think Mr. Getachew question is, we would like to ask you whether you are checking the model or not.
Sorry, sir. I couldn't
Have you
understand.
checked the model adequately?
Sir?
Have you checked the validity of your model or not?
Yes, sir. Yes, sir.
So, is it valid? If valid, justify it. Okay, ma'am. Thank you so much. Any other question? Okay, our next presenter is paper ID 07, Mr. Mustafa Usman Baba. He is lecturer in the Department of Statistics, Kano State Polytechnic, Nigeria. Are you available, sir? Mr. Mustafa Usman Baba, are you available, sir?
Yes, I'm here.
Am I audible, sir?
Yes, I'm here. I'm here.
Okay, okay. Please share your presentation.
Okay. Can you see my slides, sir? Hello?
It is still on the process. We cannot see your slide. I think it is in the process.
Okay.
Did you open it?
Yes.
Just share the slide window only.
Is it coming?
No, it's not coming.
No coming.
A serious network challenge from here.
You have to zoom out. Yeah. Mm.
Cancel that, connect to the device. Oh, you don't need to zoom in.
Please close the document first and then open it again and share to that of the meeting.
Going on.
Sir, I think this is the time to give chance to Mrs. Nafisatu Muhammad Usman, the next presenter. I request to paper ID 08, Mrs. Nafisatu Muhammad Usman, to present her work. Mrs. Nafisatu Muhammad Usman, are you available there?
She's not. She's also having the same problem with me.
Okay, no problem, sir. You can present in the afternoon.
Okay.
Sir, please stop your sharing. Thank you.
Is available.
Leave it. I think we have covered everything on the list. I am thankful to our today's keynote speaker and all participants and presenters for lighting up this session by your presence and great presentations. Now I would like to invite Mr. Sinthayo to present the certificate of appreciation to our keynote speaker, Professor Dr. Ramachandra Prasad. Mr. Sinthayo.
aiki wannan abu na network ya zama da iskanci.
Mr. Sinthayo, am I audible to you?
Am I switching afternoon night? Afternoon session. Alaikum salam. Malama. Ai na mai da mu afternoon session man. Ima network din yaki. Bayan da lokacin ya yi. Eh.
But we cannot hear him.
Mr. Sinthayo, you are not audible.
I think you have got something with him.
Okay, now this is the time for break. The next session will start at 2 o'clock by Ethiopian time. You all are requested to join the second session on time. Thank you so much. See you after the break.
Thank you, Doctor.
In Japan,